the P-38 Lightning. To this day, its twin-boom design remains one of the most iconic silhouettes of World War II. On paper, it was a masterpiece of aeronautical engineering, a fast, heavily armed, long-range interceptor designed by the legendary Kelly Johnson and his team to dominate the skies. It was America's definitive answer to the best fighters the Axis could produce. But deep within its brilliant design, in the harsh reality of combat, a deadly flaw was discovered. A flaw that turned this advanced fighter into a vulnerable target at high altitude, precisely where it was needed most. The official story of how this problem was solved credits teams of brilliant engineers at Lockheed and months of rigorous, methodical testing. But the true story, the one written in grease and sweat in dusty North African hangars, is far more compelling. It's a story about battlefield necessity, about raw intuition trumping complex theory, and about how one anonymous mechanic, with grease under his fingernails and an unwavering refusal to accept defeat, transformed a high-altitude liability into a deadly predator. This is the untold story of a mechanic's innovation. The scene is set in October 1942, over the sun-scorched, unforgiving landscape of Tunisia. A formation of P-38 Lightnings is flying top cover for vulnerable B-17 bombers at 25,000 feet. Suddenly, like ghosts appearing from the glare, German Bf-109gs dive from above, using the sun to mask their approach. The American pilots react instantly, slamming their throttles forward, trying to climb and meet the threat head-on. Their twin Allison engines roar in protest, but something is terribly wrong. As the slide says, the Lightnings claw for altitude like they're dragging anchors. Meanwhile, the Messerschmitts, lighter and more agile at this altitude, climb like homesick angels, effortlessly gaining a superior position for another devastating pass. Look at the stark numbers at the bottom of the screen. For every 2,000 feet the P-38s struggled to gain, the 109s gained 4,000. It wasn't a dogfight, it was a slow-motion execution. Pilots reported back with desperation in their voices that their engines felt like they were gasping for air. This wasn't a fair fight, it was a death sentence written in the sky over North Africa. This disastrous encounter was not an isolated incident. As the reports flooded in from late 1942 through the first brutal months of 1943, a terrifying and consistent pattern emerged. From the battlefields of North Africa to the increasingly contested skies of the European theater, P-38 pilots filed the same desperate complaints. They described exactly what you see listed here: sluggish, unresponsive throttles at altitude, and a pathetic rate of climb against German fighters that seemed to defy gravity. Above 20,000 feet, the Lightning flew like it had emphysema, a powerful metaphor for an aircraft that was literally suffocating in the thin, cold air where it was needed most. The Army Air Force's high command knew they had a critical, morale-sapping problem on their hands. Their premier escort fighter couldn't protect the bombers it was designed to defend. The best pilots and the most advanced technology were being systematically defeated by a fundamental performance flaw. Staff meetings grew tense. Memos were written, and engineers were consulted. But while the vast machinery of military bureaucracy slowly turned its gears, brave pilots were dying. The solution was not going to come from Lockheed's pristine engineering department in Burbank, California, nor from the methodical test pilots at Wright Field in Ohio. As the slide so perfectly states, it was going to come from a guy with grease permanently etched under his fingernails. A man whose uniform smelled of oil and aviation fuel, who was willing to ignore what the official manual said and trust what the engine itself was trying to tell him. His name, like so many enlisted heroes, has been lost to history, but we know who he was: a staff sergeant, around 30 years old, assigned to a P-38 squadron in North Africa that was taking a brutal, daily beating from the Luftwaffe. He wasn't an engineer with a college degree and a slide rule. He was a hands-on, intuitive problem solver. In wartime, desperation has a way of turning ordinary wrenches into weapons of innovation, and this mechanic was about to forge a solution that would fundamentally change the course of the air war. What gave this particular mechanic the unique insight to solve a problem that baffled the experts? It was his background. Before the war, he hadn't worked on state-of-the-art, multi-million-dollar aircraft. He'd worked in humble automotive shops during the lean years of the Great Depression. These were places defined by resourcefulness born from limited resources, where practical, tangible solutions always won out over elegant, theoretical knowledge. You learned to make do with what you had, a spare part here, a bit of welding there, because the customer simply couldn't afford a factory-new replacement. This Depression-era make-it-work mentality became his secret weapon. He wasn't constrained by what the blueprints and engineering tables said was supposed to happen. He was grounded in the harsh reality of what was happening, and he possessed the rugged ingenuity to find a fix with the tools and parts already in his possession. That practical, hands-on experience was about to be applied to one of the most advanced aircraft in the world, and in doing so, it would change aerial warfare forever. To understand the genius of the solution, you must first understand the intricacies of the problem. The P-38 used a brilliant, but complex, turbo-supercharger system. As you can see in these detailed diagrams, hot exhaust gas would spin a turbine, which in turn drove a compressor. This compressor would take the thin air at altitude and cram it into the engine, forcing more oxygen into the cylinders for combustion. The problem was a fundamental law of physics. Compressing air makes it incredibly hot. So this superheated air was routed through radiators called intercoolers before entering the engine's intake. But in the scorching North African theater, where ambient air temperatures on the tarmac could exceed 100 degrees Fahrenheit, the system failed catastrophically. The intercoolers were trying to cool 300-degree compressed air with 100-degree ambient air. As noted at the bottom, there was simply an insufficient temperature differential. The air entering the engine was still far too hot, meaning it was less dense. Less dense air means less oxygen per combustion cycle, and less oxygen means a catastrophic loss of power. The P-38 was literally choking on its own hot air. The mechanic spent his days and nights elbow deep in these engines, and through sheer observation, he noticed something everyone else had either missed or dismissed. The intercooler ducting had adjustable exit doors controlled by a delicate thermostatic valve. This valve was designed by Lockheed's engineers with an abundance of caution. Its purpose was to prevent the engine from cooling too quickly, a conservative engineering choice to prevent a theoretical problem called thermal shock. But men were dying from a very real problem, not a theoretical one. So he devised a solution that was as audacious and defiant as it was simple. He bypassed the entire delicate thermostatic system. He then physically locked the exit doors in the full open position, forcing the maximum possible amount of cooling air through the system at all times. And, for good measure, he reached inside the ducts and removed restrictive baffles that were designed to even out airflow but were now just getting in the way. The engineering manual explicitly said, "Don't touch it." But his modification took just 4 hours per aircraft, with no special parts. It was a crude, direct, and utterly brilliant solution to a life-or-death problem. The test flight took place on a fateful February morning in 1943. This was not an officially sanctioned test run, carefully monitored by engineers with clipboards. As noted on the slide, this was an unauthorized field modification, an act of mechanical rebellion. The pilot chosen for this risky endeavor was a lieutenant who had already been shot up twice in combat and had, in his own grim words, nothing to lose. He was a brave man willing to risk his life on nothing more than a mechanic's hunch. As he climbed into the cockpit of the modified Lightning, the entire ground crew, mechanics and crew chiefs, watched in silence from the ground. They all knew the stakes. If the modification was flawed, the engine could overheat, seize, or even explode in midair. But if it worked, it could change everything for their squadron and for the war effort. It was a moment of pure battlefield innovation, born from shared desperation and the unbreakable trust between a pilot and his mechanic. The test flight took place on a fateful February morning in 1943. This was not an officially sanctioned test run, carefully monitored by engineers with clipboards. As noted on the slide, this was an unauthorized field modification, an act of mechanical rebellion. The pilot chosen for this risky endeavor was a lieutenant who had already been shot up twice in combat and had, in his own grim words, nothing to lose. He was a brave man willing to risk his life on nothing more than a mechanic's hunch. As he climbed into the cockpit of the modified Lightning, the entire ground crew, mechanics and crew chiefs, watched in silence from the ground. They all knew the stakes. If the modification was flawed, the engine could overheat, seize, or even explode in midair. But if it worked, it could change everything for their squadron and for the war effort. It was a moment of pure battlefield innovation, born from shared desperation and the unbreakable trust between a pilot and his mechanic. Success in combat is contagious, and news of the homesick Angel flight spread through the squadron like wildfire. This wasn't a theoretical improvement discussed in a briefing room. It was a proven, life-saving advantage. Within a single week, the squadron commander made a bold and career-risking decision. Bypassing the official chain of command, he ordered that every P-38 undergoing routine maintenance receive the mechanic's modification. At just 4 hours per aircraft, the entire squadron was upgraded to this new standard in record time. The effect on pilot morale was electric. They started specifically requesting aircraft by their tail number, asking for the hot rods with the modified intercoolers. They knew this simple, unauthorized change was the critical difference between being the hunter and being the hunted at high altitude. The unofficial fix was now the squadron's standard operating procedure, a secret weapon in their fight for survival. The true test, of course, came in the crucible of combat. Over the skies of Tunisia in May 1943, modified P-38s from the 82nd Fighter Group tangled with elite Luftwaffe Bf-109s at 28,000 feet. An American pilot found himself locked in a deadly, vertical climbing scissors maneuver with a German ace, a fight he would have been forced to flee just weeks earlier. But this time, the modified Lightning stayed glued to the Messerschmitt, matching him turn for turn in the climb until the bewildered German pilot made a fatal mistake. A German ace was shot down at an incredible 31,000 feet. The numbers from the combat reports prove the staggering impact of this one change. A 42% decrease in P-38 losses during high-altitude missions, and a staggering 57% increase in enemy aircraft destroyed. The mechanic's unauthorized fix wasn't just working, it was dominating the enemy. The success wasn't limited to the North African desert. On April 18, 1943, a flight of these newly modified P-38s intercepted German Ju-88 bombers over the Mediterranean at 26,000 feet. The Lightnings were able to climb an astounding 3,000 feet in under 2 minutes to get into a perfect diving attack position. The sheer speed and aggression of their ascent completely surprised the German pilots, who were accustomed to sluggish, predictable P-38s. 3 Ju-88s went down in flames before their fighter escort could even react. The after-action report contained the crucial phrase that would be echoed up the chain of command: superior climb performance. The results were undeniable and had strategic implications. Bomber loss rates on missions escorted by these improved P-38s dropped by a massive 31%. This single modification was now saving the lives of hundreds of fighter pilots and bomber crews. By June 1943, the overwhelming combat data and pilot testimonies could no longer be ignored. Word had traveled all the way back to the engineers at Lockheed in Burbank. They finally got their hands on a field-modified P-38 that was shipped back to the States. The examination, as the slide notes, produced a mixture of profound admiration and professional horror. Admiration, because the simple fix worked flawlessly and elegantly. Horror, because it brazenly violated a dozen of their carefully calculated design protocols. The company faced the uncomfortable reality. Their multi-million-dollar, state-of-the-art product was being perfected in the field by mechanics who had never seen an engineering blueprint. But to their immense credit, Lockheed's leadership swallowed their pride. The official engineering report acknowledged the truth with a rare and admirable moment of institutional humility, stating, and I quote, "Combat experience revealed limitations in the original design that testing hadn't caught." The anonymous mechanic in the field had taught the world's best engineers a vital lesson about the gap between theory and reality. Lockheed moved with wartime urgency. The lessons learned from the dusty fields of North Africa were immediately incorporated into the P-38 production line. The P-38J model, which began rolling out in August 1943, featured revised intercooler ducting and modified thermostatic controls, a direct, official validation of the mechanic's work. It also boasted 25% larger intercooler cores for even better performance. The later P-38L model, appearing in June 1944, took it even further with completely redesigned, streamlined ducting and larger exit doors. The results were staggering, a quantum leap in performance. A 30% improvement in the climb rate to 30,000 feet and an additional 200 horsepower at altitude where it mattered most. The P-38 had finally, officially, become the high-altitude predator it was always meant to be, all thanks to a radical idea born in a desolate hangar thousands of miles from home. By the end of 1944, over 4,000 P-38s had been built incorporating the improved intercooler systems that trace their lineage directly back to that one mechanic's unauthorized innovation. His work directly influenced future aircraft designs, like America's first operational jet fighter, the P-80 Shooting Star, and validated the critical idea that field experience could, and should, outpace engineering orthodoxy. In total, more than 10,000 P-38s were produced, and America's top two aces, Richard Bong and Thomas Maguire, achieved their incredible records flying this very aircraft. The most important innovations don't always come from the top down, from boardrooms and engineering labs. They often come from the bottom up, written in grease pencil on a dirty cowling and proven in blood and fire. The mechanic was never officially recognized. He never received a medal for his defiant act of ingenuity. But as the final quote says, every P-38 pilot who made it home from 30,000 feet knew. And that's the only recognition that really matters.